And Jimmy and Roberto, if you can just keep admitting people, I think I will start us off, if that works for everybody. All right, well, welcome everyone. My name's Maddie, and thanks for joining us for this monthly EPSP Connects webinar series. My co-host today is Roberto Fernandez, and we are really excited to introduce our speaker, Dr. Haunani Kane. Haunani is an assistant professor in the School of Geographical Sciences and Urban Planning and the Center for Global Discovery and Conservation Science at ASU. And Haunani's research combines coastal geomorphology, paleo-environment reconstructions, spatial analysis, and the perspectives of native islanders to investigate how islands, reefs, and island people are impacted by change in climate. Haunani has been mentored since her youth in traditional Hawaiian wayfinding and navigation, and has spent nearly 200 days at sea aboard both traditional sailing and modern research vessels. As a Hawaiian voyager and a climate scientist, her research and teaching relies upon reestablishing ancestral relationships to place. And she hopes that through this process, she may provide a more inclusive understanding of the impacts of environmental stressors that ensure that the best available climate science data is reflective of all stories of place and their people. The title of her talk today is an exploration of the bio-geological linkages that enable or limit reef-island resiliency to climate change. And so please join me in welcoming Dr. Haunani Kane.
Mahalo, Maddie, for that introduction, and mahalo all of you for having me today, for joining in this conversation. Just gonna share my screen real quick, and here we go. So I'm assuming you guys can all see this okay? Yeah? Okay. So what I'm going to be sharing with you folks today is my postdoctoral research that I've been working on before and even now that I've joined ASU. So I've been at ASU since August, so very short amount of time. But this research has really been a collective effort amongst myself. After I finished my geology degree, I joined a coral reef lab here in Hawaii. So it's really been a collaborative effort between my background as a geologist and working with coral reef ecologists to understand what is it about the relationship between our reefs and our islands that help them to either respond positively or be impacted by changes in climate. So first, before we start this conversation, I wanted us to first go over what is an atoll reef. Here you'll see this is one of the classic images of the evolution of islands. We're using Hawaii as an example here. And I'm gonna play you this short video. But typically these islands form over a hot spot. So for example, here on Hawaiʻi Island, we are near the hot spot. Once the volcano erupts above the ocean, you have an island, and over time, as that island ages, it'll begin to submerge, it'll begin to subside, and you'll have this fringing reef that grows around the island itself. At some point, all of that basalt material will subside beneath the surface of the ocean, and you'll be left with this carbonate ring-shaped platform of both fossil reef as well as living reef along the slopes as well as within the lagoon. Deposited upon this donut-shaped fossil reef platform and also within the lagoon itself, you'll find these sandy accumulations, these cobbly, bouldery, sandy accumulations of carbonate sediment. And this is where we find our islands. So when we talk about an atoll reef island, we are talking about both the reef and the islands themselves. And we see that the formation of these islands are linked entirely to sea level change. So we talk about atolls as being this long evolutionary process, the formation of these atolls, and that taking anywhere from the island that we're going to talk about today, about 12 million years, to some of the oldest atoll islands in Hawaii being around 30 plus million years. But when we look at the actual islands that are present nowadays on these atoll, within these atolls, these reef islands, we see that they've only formed within the last, say, 5,000 years or so. And if you can imagine, when we talk about this time period that we're in, the Holocene, and we talk about changes in sea level since the last ice age, we know that sea level did not rise at a consistent rate. It rose in pulses, known as meltwater pulses. We've all seen the movie Ice Age, right? This was the whole premise behind the movie, is that sea level, the earth was warming and sea level was rising rapidly in these pulses. Well, it wasn't until the last 5,000 years or so when the rate of sea level began to slow. It peaked and it subsided. So during those 3 time periods, that we see that the conditions, both hydrodynamic conditions, as well as the environmental conditions for these ecosystems, these reef ecosystems, were conducive enough for sediment material to accumulate and build these islands. So the main point of this picture is when sea level is rising rapidly during those pulses, there were no atoll islands. When the rate of sea level slowed, peaked, and then subsided, we begin to see these atoll islands forming. And in Hawaii, we have this olelo no ea, or this traditional proverb that says, he puko'a kani aina. And when you translate it literally, it talks about a coral reef, or puko'a, growing into aina, or land, or an island. And in Hawaii, we like to play a lot on our words. So what we say is not always what we really mean, but or what we say has multiple meanings. So this can also be interpreted to describe a person growing in a small way becomes something big and strong, or the way that I like to describe it from the perspective of earth science geology is that the resiliency of our islands is dependent upon the health of our reefs. So reef islands refer to this system that's intricately linked between our reefs and our islands themselves. And also, as you can see from this picture, when you dig into the island itself, you see that the entire island is composed of material derived from the reefs themselves. So you don't see any basalt. You don't really typically see a thick soil layer. You see pretty much 100%, close to 100% calcium carbonate. And when we talk about these bio-geological linkages of a reef island system, he puko'a kani aina, what we really are talking about is our coral reefs are these sediment factories. They are feeding our islands with land, and they are foundational to the island development and its resilience. So thinking of our reefs now in this sense, producing our sediment, producing our food for our islands, they do this 2 ways. So through the framework, so through our corals, our crustose coralline algae, through cementation, binding of the reef, and then through direct producers such as the tests from foraminifera, the shells of mollusks. And then, just gonna move that there. There's erosion. We've all learned about erosion happening 3 ways. So there's biological erosion through fish and echinoderms, through urchins, literally eating the coral, eating portions of the reef and pooping out sediment, through physical erosion, through storms, and then through chemical erosion or dissolution. And then through transportation processes, this sediment is then removed from the reef and it's transported on the island. If production at the reef scale is greater than erosion, then you're said to have a net positive carbonate budget. And again, at our islands, if deposition is greater than erosion, then your islands are growing. The big question with climate change is whether or not our reefs will continue to provide this function, this same function as a sedimentary factory for our islands in the future. Whether or not our reefs will be able to not only produce sediment, but also be able to continue to grow and provide these functions as sea level rises, as the oceans become more acidic, as storms become more frequent. So we're going to take a look at least one of these questions today by looking at a storm that occurred in 2018 and looking at both the impacts and the recovery of the system following the storm. In order to do this, I wanted to first give you a little bit of a history and cultural lesson of our study site. So this is Ko Hawaiʻi Paeʻaina, or the Hawaiian archipelago. The islands here in green are the main Hawaiian islands. That's where we all live. And then as you go into this bubble, here outlined in white, you start to enter Papanaumokuakea. So it's a mouthful. I'll say it a little slower. Papahanaumokuakea. And this is a really special place for us as Hawaiian people. It's a very sacred place. The line that I've outlined here in red is Kealopolehiva Akane, or the Tropic of Cancer. And what we know about our Tropic of Cancer and our Tropic of Capricorn is that they are the boundaries of our seasons relative to the movement of the sun, right? So in the summer, the sun moves to its furthest point north, and that's the Tropic of Cancer, or Kealopolehiva Akane. And that actually intersects with one of these islands, Mokumanamana. And from a Hawaiian perspective, everything that's located south of Kealopolehiva Akane is referred to as Au. It's referred to as this living realm. And everything that's located north of Kealopolehiva Akane, or the Tropic of Cancer, is referred to as Po, as this spirit realm, as this place that our people go to when they pass and they enter the next realm. It's referred to as a space of our kupuna, or the Kupuna Islands. So when we enter into this space to do our field work and to really ask these big questions related to our future and with climate change, we enter into this space and we enter into our field work as if we would, if we were doing ceremony. So we try to conduct ourselves in the best version of ourselves. Aside from all of that, which is maybe a little heavy, Papanaumokuakea is also a marine protected area, the largest one in the US. It is also a cultural and natural World Heritage Site. And it's really important for biodiversity and for many of our species. It's the largest bird rookery in the world, and it's also home to a number of endemic and endangered species that are only found here in Papahanaumokuakea. The island that we're going to be talking about specifically today is Lalo, and the name that it was given by Westerners is French Frigate Shoals, but as we work towards decolonizing science, we're going to use the names and the traditional names that were given by our people. So let's just take a look at these names here. Lalo is the main name, and then Iho, Ae, Kona, Hele, Ho'oaniani, these are all descriptive terms that refer to the movement of the island. So Iho and Ae going up and down. Kona in the west, Hele, these islands are moving. Ho'oaniani refers to I don't know if any of you guys have been to an atoll, but if you look at the clouds, a lot of times you see the reflection of the lagoon and the clouds are actually green. And then Kane Miloha'i refers to, there's a single basalt pinnacle here at this island, and it's named after, if you've spent any time in Hawaii, you may have heard of Pele. And she's referred to as like the goddess of volcanoes and fire, but she was also one of our navigators, one of our first Hawaiians to come to Hawaii. And Kane Miloha'i was her brother one of her companions that she came to Hawaii with. And Moku Papapa refers to these islands that are low and flat. So For a long time, it was believed that this wasn't a place that Hawaiians came to, but we find in our stories and in the research of amazing people like Kekuewa who have started to rediscover these names. So one of our goals is to use them. Lalo's also an interesting place because we have documented island loss here. So the 2 dots here in yellow are islands that have been permanently lost. The islands that we're going to be talking about, East Island located here, as well as Turn Island located here. And what you're going to notice is, unlike many of the typical atolls that you may have seen in like the Western Pacific, Marshall Islands, these atoll islands are typically located within the lagoon. They are not located on a wide, expansive tidal reef flat. And then we're also going to talk about some of our reefs as well. So to give you a better idea of how we explore these bio-geological linkages, other people call them eco-geological or geo-ecological linkages, but it's all the same thing. I'm going to show you a video of our methods. And this is our team out in the field at Lalo. And what we do first typically is we excavate trenches. So we literally dig holes into the island. And from this, we're able to recover sediment. We're able to analyze the layering or the sedimentology on the layering of the sediment. And we're able to collect samples that we can determine the composition of the island as well as the age of the island. And we do this usually in relationship to what is known about past sea level and storms. We also go out onto the reef flat and we recover fossils from the reef. So I just want to make it very clear, we don't core living coral. We only core fossil carbonate. And once we get those cores, we analyze them first in the field, then we take them back into the lab, we split them. We then identify what is the reef system, the fossil reef system made up of in terms of coral, calcareous algae, foraminifera, unconsolidated sediment. And then we take thin sections of our cores as well as our sediment samples, and we look at them under the microscope, and we're able to do point count analyses. So we can determine the relative abundance of various species, genuses, etc. And then we try to tell our story. So what is the story of Lalo? So at East Island, we find that in Hawaii, approximately 5,000 years ago, there was about a 2-meter peak in sea level. About 2.7 to 3,000 years ago, the fossil reef flat within the lagoon formed. And about 1.3 to fairly recently, East Island itself was actively building. East Island formed following a central core model. So it formed in the center and then expanded. And within the last 200 to 300 years, the island itself has been relatively stable. I want to also point out in this image that these carbonate platforms here are beach rock. So they are evidence of that this is the former intertidal zone. In the intertidal zone, it's not uncommon for calcium carbonate to actually cement and to form relic shorelines. When we did both compositional as well as age analysis between these fossil shorelines and the islands themselves, there was no statistical difference. So this is relic formation of the island itself. And then we looked at the composition of the islands themselves. And what we found is that crustose coralline algae is a dominant sediment producer. So if we take a look at this 3D model of the reef system, we see that the reef system itself is predominantly coral. And when we look at the composition of the islands, corals represent just 10%. So when we think about the formation, the maintenance, and the rebuilding and the resiliency of the islands themselves, we see, oh, here we're pointing out the CCA. What we see is it's not a direct one-to-one relationship between the composition of the reef and the composition of the island. These islands are selective. They're selective in what actually ends up being incorporated into them. And it's based upon both the size of the sediment, the type of the sediment, and the hydrodynamic conditions that are conducive for island building itself. One of the things that we're working on in our lab, in the mega lab, working with our ecologists, is we're actually exploring whether or not it's possible to use these 3D models. The standard method of observing reefs in our lab is by doing photo transects, creating 3D models, and then digitizing the corals and other critters that make up the reef. So the next step is seeing if we can use this same method to also determine what is the relative abundance of sediment producers on the reef, as well as what are these rates of sediment production. And we're not quite there yet, but we're working on it. Okay, so in 2018, there was this really devastating hurricane that hit Papanaumokuakea and hit Lalo. And it received a lot of media attention because what resulted from this, this hurricane, it was the largest hurricane on record for the Central Pacific. It started off as a Category 5 hurricane. And by the time it came up to Lalo, to our study site, it was a Category 3 hurricane. 110 knots. There's estimates by our local, by NOAA, that the swells were about 10 meters or so. Folks during field camps over the summer actually had to be evacuated. So emergency evacuations to remove folks that were staying up here. And I apologize, I'm getting over a cold. But what we found was that it devastated both the reef system as well as the island system as well. So I'm gonna walk you folks through some of the research that my graduate student, Kainalu Stewart, has been working on. And we're gonna start with the islands first. So we're gonna start first with East Island, which is located here in the center of the lagoon. So this is what East Island looked like in July of 2018. So just a handful of months before Hurricane Walaka came, we were able to conduct drone surveys here of our study site. And this is what Walaka looked, what Lala looked like just immediately following Hurricane Walaka. As you can see, East Island was displaced on average about 100 meters, and it was reduced to about 5% of the size. Our analyses were done using DSAS, which is a USGS open source software to calculate shoreline change rates. What is probably most evident from this image is not only was what we see above the surface of the water, the island itself, dramatically different, but you also see that the island sediment was displaced across a large region within the lagoon, and it buried entirely this beach rock that we saw here in 2018, as well as many other features within the lagoon. It also unearthed this large fossil reef carbonate platform that for the past 200, 300 like nearly over 1,000 years, the island had been pinned to. This is an image taken this past summer when we went up to Lalo. So it took us about 3 years to be able to return because of COVID, largely because of COVID. And what we find is that East Island recovered to approximately 50%, 56% pre-hurricane size. And if you look at just the movement between 2018 and 2021, you would initially think, okay, it moved about 12 meters per year. However, what we've been exploring more recently, and this is Kainalo's work, is we've been looking at monthly shoreline satellite imagery from Planet Labs. And we've found that this imagery, at least in our current understanding of how to use it, has been both positive and negative. As you can see here, the yellow shows where I'll start from the beginning. The gray shows pre-Walaka island extent. The yellow here shows post-Walaka, and then we've colored the shorelines by year. So the end of 2018 in yellow, blue is 2019, black is 2020, and red is in 2021. And what we find is that the island recovered fairly quickly. Within about 6 months, it recovered about 35% of its size. And then within the next 3 years, it was slowly just migrating back onto the fossil reef platform through rollover processes. So this windward side of the island was being eroded and sediment was being redistributed to the leeward side of the island. So when we think about a lot of these projections that are being made about the future of our island and islands relative to future sea level, some of the big things like positive that are seen from a geologic perspective is that these islands will continue to adjust to future sea level due to both rollover. So what I'm describing here, redistribution of sediment from one side of the island to the other, as well as washover processes. So the actual waves throwing up sediment onto the island itself and allowing it to both build as well as migrate. What we've seen in the past 3 years of how these processes impacts habitats is that the habitats themselves are able to, and the species that rely upon them are able to cope. However, it is extremely difficult for, say, turtles that require 2 months for their nests to incubate to, if they don't nest in the right spot, they're going to get washed out. So what we were seeing at high tide each day was that the turtle nests were being washed out and that the uluas, or I think they're called jacks, is like the non-Hawaiian word, or trevelis, it was so cool. They would actually body surf and literally almost beach themselves and eat away at the eggs. We're also seeing that the monk seals themselves are, initially they were running into problems on these small islands where there wasn't enough space to compensate for the monk seals. And then another important use of this island was by seabirds. So it's the which I think is the booby in English, but this was an important site. I don't know if you've seen National Geographic where they have the tiger sharks and they would jump out of the water and grab the birds. So the boobies would come here, they would nest, and then it created this really cool instance where these tiger sharks would gather and they would actually wait for the birds to fledge, so to learn to fly. And they would come here to hunt birds. And it would happen every summer. But since the loss of Walaka, the birds have not yet have returned, and the sharks have not returned yet as well. So It's been interesting working in a coral reef ecology lab, as well as speaking with the resource managers from Papanaumokuakea to really understand what are the larger implications of island building and recovery processes to the entire Atoll Island ecosystem. Another thing that we observed was at Turn Island. So you can see here, we've now moved up to the northern part of the atoll. As you can see from this island, it is highly engineered. It was engineered, it's a natural island, but it was engineered in the 1940s following World War II. A runway strip was created here. Nearly this entire north side of the island is hardened. And then really the only sandy beaches are this small pocket beach here, this spit, and this southern beach. What we saw at Walaka was that there was wave overwash from the south towards the north. And what this did was it removed a lot of the vegetation. So there was actually shrubs that were on the island prior to this, and those shrubs acted as a barrier that that helped turtles to know that they hadn't gotten too far up onto the island and that they were in healthy nesting zone. We also find that the wave overwash elevated portions of the island. So this is a turtle nest seen in 2019, a year after Walaka. And you can see the pre-hurricane soil layer and the sediment that's deposited upon it. And this nest was abandoned by the turtle when it encountered this hurricane soil layer. When we returned in 2021, we dug a series of trenches across the island because we wanted to know how much sediment was deposited by the hurricane, but we also wanted to know if the composition of post-hurricane sediment or this wave overwash was the same as the original composition of the island. And here we see that on the island that there was approximately half a meter or so of overwash. And in terms of the compositional analyses, that's something that I'm working on right now. So stay tuned. And then when we take a look at the reefs themselves, what was the impact of the reefs upon the reefs? This is an image of an iconic reef, Rapture Reef, located in the southern region of Lalo. We see that prior to Hurricane Walaka, the 3D models and orthophoto mosaics reveal that the reef itself was comprised of approximately 70% acropora coral. And post Walaka was converted, it was completely obliterated and converted to 99% rubble and sand. What we find though from this past summer's research cruise, and this is the work of Atsuko Fukunaga and Kylie Pasco, is we find that 3 years post Walaka, we have coral recruits, predominantly Postulopora, that have started to emerge. In Hawaii, this is one of those species that Postulopora meandrina that emerges following disturbances. And it's also been shown that they have been successful in colonizing on rubble beds. We also begin to see that binders are starting to emerge, so sponges. And when you think about when reefs start to get binded together, that sponges are typically an immediate phase binder that's followed by more predominant binders such as crustose coralline algae. We also see that rubble presence relative percentage has increased and sand has decreased. So sand is being exported from this system. And another great thing that's really good to see is that reef fish surveys were conducted in tandem with the coral reef surveys, and the reef fish themselves are starting to return. So thinking and moving forward with planning for the future of a resilient lalo, we've been doing a lot of work talking with the resource managers. And one of the things that we see is when we've got to like really start at the beginning. We're talking about reefs, and we're realizing that we're all talking about different functions of a reef. So the coral reef ecologists are, they're thinking about habitat and structure. They're thinking about biodiversity. We've started talking with chemical oceanographers as well, and they're thinking about this in terms of calcium carbonate, but not in the same way that I'm thinking about calcium carbonate in terms of sediment. They're thinking about their carbonate budgets themselves and thinking about dissolution and how climate change in the sense of like acidification is going to start to impact these species. And then when I jump in, I'm like, wait, how is acidification going to impact the sediment within the island itself and the transport of that sediment and the quality of that sediment? So it's really interesting as like scientists, we're starting to have these conversations and thinking about when we talk about resiliency and we talk about the functions of reefs, we're talking about them from different perspectives, but we're really learning a lot together. We're also having more discussions with the resource managers in terms of like, how does island recovery impact island resources? So if we have an island that is able to bounce back from, say, a storm, or can keep pace with sea level through wave overwash and rollover, but the resources that rely upon the island are having trouble with those same processes, is this really a functional, healthy island? And if not, then what steps are going to be taken to possibly engineer or harden islands? And is that even the best approach to this solution? Or should we be talking about relocation of these endangered and endemic species to the main Hawaiian Islands? And relocation of seabirds has begun already. Another thing that's really exciting for Papanaumokuakea and envisioning what a resilient lalo or resilient space could look like is the release of my Kapomai. So a native Hawaiian guidance document was just released last year. And this will help to ensure that as we begin to think of the future of these islands, that we're also thinking about it from a cultural perspective as well. So yeah, so that's what I have today. Please let me know if you guys have any questions or thoughts. I'd really appreciate that.
Thank you so much, Haunani. If we all want to take a minute to thank our speaker. And Roberto and I can now, we got some questions in the chat. Thanks so much. And we'll take turns just reading them off. If people also want to raise their hand or unmute to just ask their question directly, that's totally fine as well. And it seems like the first question we have here was more of a comment, I think, from Theodore. Mentioned that the upwelling of colder water seems to help the coral at and near the drop-off. This came in kind of earlier on in your talk.
Yeah, that was a comment on about coral bleaching. So it wasn't too relevant to your talk, as it turns out.
No, thanks for engaging still. Tori asked a question, intertidal zone remnants. What is the difference between beach rock and subsiding or fossilized reefs coming from a landlocked state? Do you want to talk about?
Yeah, thank you for that question, Tori, and my apologies for not explaining it better. So beach rock is literally what it sounds like. It's when beach, unconsolidated sediment gets cemented and into a rock, and it's cemented in place. So we use that as a marker of former shorelines. Fossilized reefs typically are corals that are in place. So they're where they grew. And you can find sand within them that does become cemented, but typically the beach rock itself is just a shoreline, so sandy sediment that gets cemented into rock. And Ron, he he made some good comments here about cements that you'll see as well. So there will be variations in the cements themselves between the coral reef as well as the cements that hold the grains of sand together.
Okay, so I assume that's in reference to Ronald Dorn's comment in the chat.
Yeah.
Yes. Okay, so next question is regarding the use of planet imagery. Did you use it to look at East Island before the hurricane? Just curious if there was any variability noticed prior to Walaka, or if it was strictly the result of the island bouncing back.
Yeah, shucks. I should have included a slide of that. So we also did a historical assessment of shoreline change prior to Walaka from 2007 to 2018. 2007 is about the oldest imagery that like high quality imagery that we had available to us. And we did see that East Island was in an erosive state. And I can't recall off the top of my head exactly what the rates of erosion were, but it wasn't anything that's like super dramatic. So we did look at shoreline change prior to Walaka, but what we're seeing following Walaka is largely just the island recovering and moving back to where it was located on the reef platform prior to the hurricane.
Thanks. Next question came from Tori. Can you identify the hurricane or storm deposits in the core you took, or the trenches that you dug? I'm wondering what the composition looked like.
Yeah, so that's a good question. Prior to the hurricane happening, East Island was just described as this amazing, magical, beautiful place that was super stable and didn't really change much. And I'm going to try to get to an image here. But short answer, no, we could not identify any storm deposits within the islands themselves. If you look at this image here, you can see that when you're looking at strictly just carbonate, it's really difficult to see or identify layers such as storm deposits. We've worked in wetlands where wetlands that are backed from a beach, and it's a lot easier to identify storm deposits, hurricane deposits, even sea level signatures, because you have the introduction of a different material, say the beach sand, into wetland peat. When we looked at this here, and we looked at the grain size, and we looked at even the composition, for the most part, the composition is fairly homogeneous. It's dominated by this crustose coralline algae. It'll be interesting to see what the island looks like post-hurricane, and maybe using that as a proxy, we might be able to make comparisons with pre-hurricane to see if there are discrete layers within the island itself that could be representative as storm deposits.
Okay, there's another question, but I'd like to ask Tori, would you be able to tell us if the last question is in regards to the one that Haunani just answered or to the second one? There's to follow up hurricanes from before 2017 as well. So I'll ask the former question and then they can tell us, will your work expand to other atolls in Papahana Umukuakea?
Yeah, so definitely that is a goal. When we look at the geology, like the work that's been done up there on the islands itself, a lot of geology, like marine geology has been done, but on the islands themselves, the last time there was any sort of geology was in the early 1900s. So what we know about the Sandy Islands from a geological perspective in relation to sea level and whatnot is still very poor. This is the first study there. We're just kind of scratching the surface. And in terms of prior hurricanes, what was so unique about Hurricane Walaka is it's the first hurricane on record that has gone that far north. So, this, I don't know, we're really kind of at that tip of the iceberg where is this new track? Is this going to become more of a norm as the ocean warms? We are anticipating a greater frequency and intensity of hurricanes here in Hawaii. And whether or not, to my knowledge, I'm not entirely sure if that will include the islands up in Papanaumokuakea as well, as many of those islands extend beyond, like as I showed, they're north of the Tropic of Cancer. So that'll be interesting as well.
So maybe the follow-up was to this question, if there is interested as well to look at hurricanes from before 2017 as well.
Great. I think that I have a question for you, Haunani, if that's okay.
Yeah.
Tori, just feel free to follow up in the chat if we didn't quite address your question. So kind of like building off of Kenzie's question about the planet imagery, it seemed like having that monthly resolution was really important for seeing these really important dynamics that are going on that otherwise you would not have noticed. And I'm just curious about the data availability in the region and like what you need or like what data you're interested in collecting to like help further your research. Is it just like more research or more like surveys, like going out on boats, or is more remote sensing imagery really been helpful? You can just talk about that. That'd be great.
Yeah. So it's really been interesting learning through this process. Like, that's such a great question. What is it that we need in order to understand these processes? Because I've been kind of operating, like as a young scientist, learning to go out into the world on my own. It's been a lot of trial and error. When we first started in 2018, we were able to fly our drones up there. Since then, because it's a national monument, there has been a memorandum where you can no longer fly your drones up there. And that's mandated by the Fish and Wildlife Service. So that has been particularly challenging, is the ease of getting highly accurate imagery while out in the field. With the drones, we can get about centimeter resolution imagery. With satellite imagery, you're getting anywhere between 1 meter to 3 meters. And really a lot of information is lost with that sort of resolution. What we are really, really excited to, we've applied for additional funding, is the ability to go up on our research cruises, geologists and ecologists on the same research cruise. the past handful of cruises that we've done, we've been on separate cruises. I like to sail, so I'll take a sailboat up there with our team, but that doesn't allow for scuba diving. So getting creative about if we're gonna go up sailing, we need free divers to do our coral reef surveys. If we go up on the larger boats, then we gotta take our geologists with us. And really starting to create more of the marine surveys, the coral reef surveys closer to the islands, because in the past, they've really targeted reefs that are along the rim, typically, a lot that are not located adjacent to islands. And I'm really interested in getting surveys closer to the islands and also trying to better constrain those erosive processes. So working with a chemical oceanographer as well as an ecologist to understand processes of dissolution, as well as really trying to get a better hold on our bioeroders as well.
Thanks so much. And Kurt just shared a great link for a way of getting around not being able to use drones and using kites instead.
Oh, cool. Thanks, Kurt.
Yeah, we ran into the exact same problems. So
yeah,
both balloons are truly wind-driven kites. So something very easy.
Oh, awesome. Yeah, thanks for that.
And then we've got another question from Hugo Salgado. Thanks for your presentation. 2 questions maybe. For Lalo Island, both for their foundation and resilience, what is the role of the pre-existing topography? For example, Paleocars or paleosurface exposure?
Yeah, that's a really good question. And I don't really know if I have the best answer. We're also finding that each of our islands are responding fairly differently, even on a seasonal scale. We have other islands, and I wish I put a picture there. They're called the Gins. We're working on getting them renamed. But we see that on these islands, they were really weren't really affected by Hurricane Walaka at all. And what we see here is that these islands each month are moving and they're swinging around this like pinned center. And because of that natural dynamic process, I think they were able to respond a lot better to Hurricane Walaka. And I'm also interested in knowing if that was related to the reef platform itself. In terms of Paleocars or paleosurface exposures, when we worked in Majuro and we had these large reef platforms, these wide reef platforms that were exposed daily at low tide, we saw more of those, more of an environmental signature from being exposed to the atmosphere. However, much of the reef platform that these islands sit upon, they're not intertidal, they're not exposed at low tide, and they are still submergent. So, so that's a good question. And in terms of satellite images, I'm sorry, I cannot help you with that, but maybe somebody else in this room might be able to.
So you've mostly used Planet Labs. Their resolution is what, 1 meter?
No, so Planet Labs, Kainalu, who I believe is here, he has used it a bunch. And we found some success with it. It's 3 meter resolution. The images themselves are not, they're not always georeferenced all that great. So one of the big things that we've had to do is we had to actually correct our satellite imagery. We've had more success with using worldview imagery. You can get imagery that's under 1 meter resolution, but Planet Labs is free. Worldview imagery is typically not, unless you're a federal employee. Yeah.
So I think Kurt might have something to add to this.
I was just typing it right as Haunani said that. So,
All right.
one thing that just to let folks know is for the U.S. Office of Naval Research, we're actually developing structure for motion from satellite.
Cool.
And so while we will not, Haunani, get down to the decimeter or centimeter scale, it will hopefully allow us to start to try to do some of these morphologic studies, especially these outer islands, whether it's the northwestern Hawaiian Islands, Republic of the Marshall Islands, Federated States of Micronesia, to be able to get some of this topographic information.
Yeah, and that really is a good point, because many of these remote islands, they don't have digital elevation models, and they don't have like the bathymetry itself is not that great either. And as you can see from our project, you can have one storm come through, and the bathymetry of a site can be drastically changed with how much impact you see, both from the destruction of the reef as well as the movement of the sediment as well. So I think something like that, Kurt, is going to be really helpful for many of these remote places.
I think that might be our last question, just because of time. Roberto, do you want to close up our?
Sure. I just wanted, if Haunani is okay, hopefully if she can give us a 1-minute answer, if someone posted in the chat, if there might be any opportunities to join this work and help. And then
Yes.
I also wanted to add that you mentioned things that are quite relevant: decolonizing science, considering the people, etc. Would you be able to give us like a quick set of things that we should consider if wanting to do field work in this area? Should we approach certain communities, etc., given the places are sacred? I think it'd be very useful for those of us here and for anyone who might see this recording later.
Yeah. So this past summer, our field work was pretty amazing. We were able to sail up there with our students on a sailboat. The trip itself took about 2.5 weeks. And we did all our field work. We engaged in protocol. We came home safely. And I am really, really hoping that one day, like something like this can be a class that I can offer for credit. There have been similar classes like that offered here in Hawaii to Papaʻanamokuakea, never by sailing, but by flying on an airplane. I think it'd be amazing if we could sail and do field work. So that's my dream. That's my goal. Hopefully we can make it happen. And in terms of thinking about the ways that we approach science and how we engage community, I think there's so many ways to do it. In places like Papaʻanamokuakea that were established, both with culture in mind, there's already like great frameworks set up. There's a cultural working group. There's a lot of information on the website. I would also encourage you folks, when you start to work in places, to do research before you go there, to look at who are the native people, the first people of that place. What is their language? What are the traditional names that they use? And something that I would like to be better about if I do start doing fieldwork outside of Hawaii again, is I would like to be mindful in even reaching out to some of the schools that are in the places that I might work, and see if there are students from there that would like to join in the field work. Because in that sense, they can learn tools, they can start to imagine, dream, think big picture about some of the problems that they're facing and some of the solutions that might be out there in order to solve them. And that way they're in-house, it's located there, and can help build capacity as well as learn from them. So those are just some of my thoughts.
All right, thank you. Thank you very much for your excellent talk and for what we've been able to learn. Thanks everyone who tuned in for the talk. Our next EPSP Connects will be on May 18th at 10 a.m. Central US time. We will have Dr. Nate Jones from the University of Alabama, who will give a talk entitled Incorporating Watershed Storage, Hydrologic Connectivity, and the Natural Flow Regime into Water Resources Management. Keep an eye out for the official announcement and the link to the talk.